Thank you very much. Hello everyone, and thank you, Dominic. My name is David, and I'm going to present you our design of a new test configuration for in-plane shear on timber elements. This research was carried out in close collaboration with my dear colleague Niels Schumacher, who couldn't be here today, unfortunately. But it's okay, because that's the topic of my PhD thesis. So let's start. Let's start with the question, why do we need a new test method at all? And yes, there are already a lot of different types of shear testing in the literature. This is one example. It's called the diaphragm shear test, which is outlined in the Annex C of the standard EN 16351. And this one works perfectly well for CLT. But no known method yet is suitable for testing all variations of wooden elements. They are all limited to specific products. Even this diaphragm shear test setup has one problem. The resulting stress state, it's shown here, is always under compression because of the force. Here and here, we have always compression. That means if we use any other angle in the laminated timber than 90 degrees, this will result in stability failures instead of shear failure, and we don't want that. This is why picture frame tests already exist as a testing method, so that's nothing new. The idea behind it is to use an hinged steel frame. You see it here. And this frame transfers the compression load into a load that's linear to the edge of the test specimen. And because of that, the resulting in-plane shear stress would be pure and without any compression. So that's the state we want. And on top of that, as long as we stay with small displacements, we can calculate the resulting shear stiffness and the shear modulus using simple geometry. It's here in this equation, because the shear modulus is the shear stress divided by the shear strain. And in this process, we even can calculate the shear stiffness here. It's the force divided by the displacement, the delta. And one important thing is we have the active direction, it's the direction of the force, and the passive direction, it's perpendicular to the initial force. Yes, and so the most important thing about the picture frame testing is how is the load introduced into the test specimen. And that's why we invented a new approach. We use those notches here. You see it in the graphic here in the detail. Those are the key element of our new test method and the novelty of our approach. No one else did that as we know. And they look like, they're quite small, only 80 millimeters long and 26 millimeters deep. There are 9 notches along the edge, so it makes a total of 36 notches. And they are oriented to for the vertical compression load. So we have vertical load and load introduction downwards and upwards. Yes. The result is, first of all, one disadvantage, because the test specimen gets a lot more complex in the form with all its edges and corners. So those small notches we have to create in test specimen, they are not easy. But we hope for one huge advantage compared to all other available methods, and that's the notches should allow tests with all kinds of elements. Not only with diagonal layers, but also with mechanically jointed elements, as well as the usual glued CLT. So we should be able to test everything in this frame. So we had to prove our concept by practical testing. And therefore, we used 3 different kinds of specimen. First of all, 5 panels of 3-layer CLT. Then on top of that, we tested 3 panels of 5-layer CLT. And to check the full abilities of the frame and of the notches, we used 8 specimens of mechanically laminated timber. And these even had 2 diagonal-oriented layers. It's here in the table. One had 30 degrees and one had 150 degrees angled to the top layer. So, and this is how the final test setup looked like. We measured the displacements in the central area of the specimen. So here in the middle. The side length, this length, was half as long as the load introduction length, so the whole length of the frame leg. We used 2 different setups to measure. Side 1 with 2 cable displacement transducers, one in active and one in passive direction of the vertical compression load. And on the second side, the measured area was captured with a digital image correlation system. That is why we used those white surface with black points on it. So here are the results. Well, the first of the results is the 3-layer CLT. With all of the 3-layer CLT, we achieved a net shear failure. That is typical for non-edge glued CLT, so that's good. The shear stiffness and the shear modulus were evaluated in the elastic range between 10 and 40% of the maximum load, so somewhere here in this area. And yeah, when we look at this figure, we can see that the active direction, so this is the force, the displacement, the vertical displacement, we see that it's slightly higher than the passive direction, resulting in a lower stiffness in active than in passive direction. Overall, shear modulus of 526.6 megapascals was measured with those elements. How we have to evaluate this comes later in the conclusion. Here are the results for the 5-layer CLT. The same thing with the higher displacements in active direction is true for those elements too. Here the difference is that the 600 kilonewtons of the testing machine were insufficient to cause failure of the specimens. However, the specimens showed already initial signs of net shear failure, even if they didn't fail in the end. And here the mean value of the shear modulus was calculated as 561.5 megapascals. And then the last one, the results of the mechanically laminated timber. These tests worked out well, and in all specimens the typical torsion failure of the joints occurred because they were only jointed with nails. But during this tests, the displacement in active direction was much higher than in passive direction. You can see it even here in the graphic. It's a much higher deformation. And on top, the difference between each specimen was quite high. As we see here, the coefficient of variance goes up to 30%. So the mean value of the shear modulus of 100 megapascals it's not. It's much lower than the CLT, and with a quite high variance. This brings me to the conclusion. Based on these results, the conclusion I take is that the test setup we investigated was successful. The failures, the stiffnesses, the shear moduluses we achieved for the CLT seem plausible, especially when compared with values from the literature. Here I have listed some of them. The 527 and the 562, they fit quite good to the rest of different types of testing methods. The tests with the mechanically jointed timber also worked out well. However, no comparison is currently available, so no one else did tests like this with mechanically laminated timber. So I can't compare them right now. That's why even more tests are necessary. And that's what my next steps will be, to conduct even more tests, more and more and more, and make direct comparison with other test methods, like the diaphragm shear tests I showed earlier. And well, in fact, that will happen next week. And yes, the overall goal is to validate the new test procedure and to determine all its possible applications and limitations. Yes. That brings me to the end. Thank you for having me. Feel free to ask.